Hello, everyone. My name is Eran Gilad, and I'll be talking about parallel programming models in C++. This being the very last session of TechTown. I appreciate the fact that you're still around. I know you're all in a hurry to get back home, so thanks for staying with me. So a little bit about me. I started my first job in a small company called IDEA, where I was the only C++ developer, or the only developer that used C++. And during that time, quite a few years, I developed a taste for community events, mostly user groups meetings, which were actually the only way for me to meet other C++ developers. So after a few years, I went back to grad school, obtained a PhD from the Technion, Israel Institute of Technology. And towards the end of my PhD, I co-founded the Haifa C++ meetup group, which was the first C++ meetup group in Israel. After graduating, I started working at Yahoo Research, and around that time, I joined the organizing committee of the Core C++ conference. Core C++ is the other meetup group in Israel. So, why do we care about parallel programming? First and foremost, it gives us performance. Okay, we can utilize more compute resources. We can also use parallelism to hide latencies introduced by I/O operations, and we can keep our UIs more responsive. Why is parallel programming hard? Well, it introduces non-deterministic execution, so subsequent executions might yield different results. And it also introduces some issues such as data races and deadlocks. And therefore, having a structure in our parallel programs can make things much easier. So a programming model provides some holistic structure into our programs. And that structure allows us to use some very useful abstractions. Those abstractions allow the user to better reason about the correctness of the program on one hand, and on the other, the library, which has a better idea about what the user is doing or trying to achieve, can provide useful features. At runtime, since the library has a better idea about what we are trying to do and trying to achieve, it can better optimize the scheduling and the execution of our program. So both ends, the compile time, correctness, and the runtime performance are crucial in parallel programming. Now, C++ offers a plethora of parallel programming facilities. I've listed just a few here, and there are many more. This is neither a random or arbitrary collection, nor a single API for parallel programming. Facilities can be categorized into 3 different parallel programming models, which I'll introduce in this talk. The first programming model is what I call unstructured, which is kind of a contradiction, but bear with me. And the unstructured model means that you implement your own parallelism mechanisms in your program using the lowest level mechanisms such as thread, mutex, and atomics. And this model was introduced in C++11. The second model is task-based, which uses async promises and future, introduced also in C++11. And lastly, the data parallelism, which relies on the parallel algorithms facilities that were introduced in C++17. Those different models are not different abstraction levels. They are a completely different way of structuring your parallel program. So the outline of this talk after this brief introduction is as follows. First, I'll describe three different programming models. Then I'll compare the three. And finally, I'll discuss mixing different models. This talk is about the forest, not about the trees. Namely, I'm not going to deep dive into a lot of the details of the different APIs, but rather try to describe the model itself and how it can be used. During this talk, feel free to interrupt me through the Slack channel or the WebEx chat, and I'll try to answer as we go, or we can have a Q&A at the end too. So first model is the unstructured parallelism model. This means we're using, in this model, this ad hoc use of the parallelism facilities. Namely, the structure is not determined by the language level API and facilities, but rather by the particular use that you find appropriate in your program. It relies on the lowest level abstraction. This means you have, or you can have at least, minimal overhead and maximal hardware utilization. But on the other hand, it provides a minimal amount of safety. So you really need to know what you're doing. Otherwise, you'll get into trouble. And this model, as I said, was introduced in C++11 and provided some of the central features of this language version. So the major components of this model are, at the lowest level, the memory model itself, which includes atomics and thread local. Above that, we have the threading and synchronization classes, such as thread, mutex, conditional variables, and the newly introduced in C++20 semaphore, latch, area, and others. And above them, we have convenience utils, such as the RAII lock wrappers, call once, and the newly introduced JThreads. And this forms the basic facilities that we can use for this model. Some use cases that are exclusive for this kind of programming model. First is construct higher level facilities. For instance, we can create a thread loop or a spin lock. Second use case is implementing concurrent data structure, either thread safe but lock based using mutexes, or even better, lock free data structures using the low level atomics. And we can also use threads for some long running services in the background. The missing part in this programming model is a safe shared state. So when we launch a few threads, the way for them to communicate is via some sort of shared state, either global or one that is pointed by various threads. We can manage that state using atomics, but that can be a bit too fine-grained and hard to get right. And we can also use locks to make existing standard containers thread safe, or for this kind of locking can be too coarse-grained and reduce the amount of parallelism we can obtain in our program. So when we need is concurrent data structures. And this is being currently considered, nothing big yet, but hopefully we'll get in the upcoming versions some facilities such as thread safe queues, hash maps, RCU data structures, and so on. Finger crossed. So the unstructured parallelism has a few advantages and disadvantages. First of all, we get maximal control because we are using the lowest level API, and we can possibly get the maximal performance if we manage to get things right. On the other hand, it relies on a very complicated memory model, and getting things correct is indeed pretty hard. And when you don't get things right, then you experience fun stuff like data races, deadlocks, and non-deterministic results. So the thread level API itself has a few shortcomings. A thread in general is an abstraction of a processing. Okay, the thread gets when it is launched an execution entry point. Much like when you start a program, then you get a main that starts your program, and the thread itself does not have any functional semantics. Further, any synchronization among different threads or communication and scheduling, they are all interleaved in the code that you're running with that thread. Okay, so this is up to the programmer to manage, and it is interleaved within the parallel thread logic. What would have been nice is if we can have some higher level abstraction and some clever runtime that will allow us to do less work and obviously have less bugs and potentially get better performance since this is done better. And this kind of solution is provided by task-based parallel model. So tasks are computations that are usually limited in scope and provide a single result or none. They can be functions, lambda expressions, loop iterations, and so on. And ideally have input and or output, but no side effects, namely as little interaction with global states. And the good thing about tasks is that they decouple functionality from execution. So you specify the task itself, and some runtime executes it in a abstracted way. So one thread can be used to run many tasks on one hand, and on the other hand, one task can sometimes migrate between multiple threads. And this is not something that the model exposes to the programmer. Tasks are asynchronous, namely the creator creates a task. It is then executed somewhere, sometime on some other parallel or some other compute resource. And the creator can proceed, do other stuff until it actually needs the result of that task, at which point it can wait and get the result. And communication between the creator and the task is done by a channel that has two ends. The creator end of that channel is called the future, which is basically a handle to the outcome of the task, if one exists. And on the task end, the end of the channel is called a promise, and this is where the task sends the result to. So in C++, tasks are launched using std async. Okay. When you make a call to async, it returns a future, and via that future, you can obtain the result once the task is done its computation by calling future get. Okay. the runtime can assign the tasks that you create through async to different worker threads. And this is something that can be a bit surprising for folks coming across async at the first time, on the first time. And the somewhat surprising thing about it is that the runtime here, the C++ runtime, which has to be as efficient as possible, can actually create and manage thread pools without the user having a lot of control about it. Okay, so if you call async once, you might have a thread running in the background even after it returns. Now, the actual execution of the task is determined by the first argument provided to the call to async. And that can be, and there you have a few options. The first one is pass launch async, which means the task is going to be executed on a new thread, or better put, as if on a new thread. Async does not necessarily launch a new thread, okay? And one should not use async to try to launch a new thread or get a new thread, because it can use an existing thread that's from an internally managed thread pool, if one is available. So it merely means the task is going to be executed on a separate thread from the one that is on which async was called. The second option is launch deferred, which means that the task is going to be executed right before the result is needed on the very same thread that's called async. So here, the task is not going to be executed until you actually need the result, and no other thread is involved in the execution. And if you do not call future get, then the task itself will not be executed. So this is just deferring the execution of the task. And lastly, you can combine async and deferred, which is actually the default when no policy is specified. And in this case, the behavior is implementation dependent. The runtime can decide whether it's more appropriate to run or execute the task on a separate thread, or just defer the execution until the result is needed. So as said, the result of a task are delivered through a channel that has two ends. On the caller side, we have the future, which provide access to the task result. And it's basically the pull end. And on the task end, we have a promise, which is the push end. And importantly, you do not see the promise itself when you create a task using async. As you saw, you specify, say, a lambda expression that returns some value, and async stood async moves that returned value into the encapsulated promise. So there is a promise within the channel, but it's not exposed to the user that uses async and futures. If you do want to use tasks, but you do not want to use async itself, you can use a class called package task, which allows you to wrap some executable using a task object. From that task, you can get the future, which will again be the end of the channel that delivers the result of the task. And at this point, we're still working on the same thread, same caller thread. Then we can create a new stood thread and pass it the task instead of using async. Do some useful work, and then again, call the future get and obtain the result. So this piece of code here is similar to async, but without the async itself execution. So if you're not happy with what async provides, say you want to implement your own thread tool or so, you can use package task to obtain at least part of the functionality. Yeah. So, as said, C++ provide a task-based programming model. If we consider some well-designed task model to be this beautiful horse, then what would the C++ task model look like? I say like half a camel or so. It is missing a lot of things. It misses thread pool size, or more generally, an execution context that the programmer can control. It misses composition of tasks. It misses cooperative scheduling, and so on. Now, the parallelism TS1 does provide some extensions to futures. First, it provides future.then, which allows you to chain continuations to a certain task. So you create a task using async, you get a future, and then you chain some other task using future.then, and that task gets executed once the future completes and the result is ready. It also provides other facilities such as when all, when any, which allows you to chain tasks to a set of tasks. Unfortunately, those experimental features are kind of on hold due to the following reason. We have coroutines and executors on the way. So coroutines introduced in C++20 are, in short, a mechanism that allows functions to be paused and resumed from the same location or with the same state in which they were paused. And once those functions are paused, you can do other things. And this is a great feature to have for a task-based model. Let's say some task is executing and it's now being stalled, waiting for, say, some lengthy I/O operation. Instead of keeping the thread busy and a processor busy while it's stalled, it can just notify the scheduler, I'm stuck, let someone else execute and resume my execution when I'm ready. And that can be done using the coroutine mechanisms. So the task cooperatively gives up the execution context, moves aside, let the scheduler execute some other task, and when it's ready, it is resumed from the exact same state, which is something coroutines provide. So coroutines provide one nice building blocks for tasks. Executors, which have not been approved yet and hopefully be added to the language in C++23, provide a way to define execution context. So the immediate example is some thread pool. Okay, you as a user, you can say, I have 8 cores, but I only want to the task-based model to use 4 of them. Then you create a thread pool with only 4 cores, and let the async use that thread pool. Okay, so for a well-designed task-based model, and since both those features are either newly introduced or not yet introduced, there's no real point in extending async at this point of time until the other mechanisms are available. So to wrap this up, let's compare threads versus tasks in general. So first, threads, the use cases that can be appropriate for threads are background services, long and complex parallel operations, and when you have an equal amount of per-thread work, okay? Because you want, if you're using multiple threads for some computation, you want them to complete their work roughly at the same time, so you get decent load balancing. On the other hand, you want to use tasks when you have many short and independent operations, not necessarily doing the same thing. When those computations are defined pretty much locally using, say, lambda expressions, and tasks provide dynamic load balancing. So you can create a lot of them, and you can trust the task scheduler to make sure that your resources are utilized in a sensible way. As for stud threads and stud async, so stud async provides better resource utilization when the task scheduler is properly used. It provides a clean return value mechanism through futures. It provides exception safety. Okay, if a task throws, then that exception is propagated to the future. It provides timed waiting. You can wait on a future with a timeout, unlike the thread joins. And it provides multiple accesses to a future, unlike a join, which you can't recall multiple times. Threads, on the other hand, mostly provide a deterministic execution context, which is a separate thread. Okay, so moving on to the third programming model, which is data parallelism. So in this programming model, parallelism stems from the individual computation associated with every element in a collection, okay? This means you have a collection, or in general, a lot of data that is mostly non-dependent, and the algorithm can divide the work among different processors and execute the processing in parallel. The general structure of parallel algorithm includes the following components. First of all, the algorithm itself is called from a sequential execution context. Okay, you do not need to launch any parallel threads or something. Then you define the execution policy in a declarative way. You just say the desired policy, and the algorithm itself takes care of the rest. And you provide the container whose processing you'd like to accelerate by doing it in parallel. The parallel algorithms are a high-level abstraction. Okay, so you have a few customization points that you can use. You have no control over the amount of parallelism, the scheduling of different threads, and how work is being distributed. On the other hand, giving those restrictions and abstractions, the library in the runtime can be very efficient. And when you use it properly, you're free from data races, deadlocks, and all those bad issues. Parallel algorithms were introduced in C++17. Their adoption has been slow in terms of compiler support, They're currently only supported in GCC 9 and Visual Studio 2017 later editions. And also available as library implementations provided by Intel or CodePlay by their SQL library. So how do we use parallel algorithms? So first, most standard algorithms have a parallel overload, and that's specified in the standard. The first argument that you provide to a parallel algorithm is the execution policy, okay, which I'll discuss in a minute. And another difference between the regular algorithms and the parallel ones is the type of the iterators that you provide. Okay, so in the sequential algorithms, you provide input and output iterators, while in the parallel variants, you provide forward iterators, which differ in being able to recall them or store a forward iterator and re-access it, even if it has moved on, which is important for distributed data among different threads. This is a bit important because if you're trying to move from a sequential algorithm to a parallel one, and you just add an execution policy, then your code might not compile because of the type of iterators. This is not, this is not by accident. It's sometimes something that you have to really change your program for. As for the complexity requirements, then they are a bit more lax on parallel algorithms because parallel implementations might have to do more work for the parallel processing. However, this a little bit of extra work allows them to process the data in parallel, so the overall performance is expected to be better. The actual implementation of the parallel algorithm as the sequential algorithm is not defined in the standard. So in theory, you can use different kind of algorithms, and you can use, or sorry, the platform can use different processing resources, such as the GPU, if it finds it appropriate. So the first parallel processing policy is called sequence policy. And what it means is that the parallel algorithm is actually going to be sequentially executed on the calling thread, okay? And so using the sequence policy differs from the non-parallel algorithms in two ways. First, exceptions invoke should terminate. This is the case with any parallel algorithm, and even if it is executed sequentially. And the second difference is, again, the use of forward iterators. Now, to specify a policy, you provide the algorithm with an object which is an instance of the policy type. So the instance of sequence policy is called execution seq. And the idea is that each object like that has a different type, and this allows algorithms to be overloaded according to the different policies they implement, okay? And this means that the policy specification is a compile time decision, okay? Even though you pass an object, you can't make that a runtime decision because the type of that object is defined in compile time. The second policy is called parallel policy. And the execution in this policy is done by multiple threads as determined by the runtime scheduler. Here, per thread processing is like the sequence policy, namely each thread processes a single data element at every given moment. Okay, it does not process, it does not interleave processing of different data elements by switching among them. The order of elements that is being processed by each thread is not specified, but again, it is guaranteed that each element is being processed in the full by a single thread. Okay. Now, within each thread, if you execute your own code, say by using something like for each parallel, data races are possible if you access some external state that is not protected. Okay, as with any kind of parallel execution that is unsafe. However, if you're not accessing that kind of data, any access to the processed container is guaranteed to be safe. The third policy is called parallel unsequenced. And here, a few more restrictions are provided or required. So here, a single thread might process multiple data elements at the same time, or at least potentially do that. And data elements might be processed by multiple threads. So this poses some restrictions on the code that you may write or may provide as the user. For instance, you may not use any locks, okay? And you cannot assume that a thread executes a single operation at any given time. Those are some formal requirements that are a bit difficult to understand, but what you need to have in mind here is the following. Using this policy, or the restriction imposed by this policy, allows vectorization to be used. Okay, so basically, the goal of those restrictions is to make it possible for the implementation to safely have a single thread process multiple elements at the same time using vector instructions. Okay. And the last execution policy is called unsequenced, which is included in C++20. And according to this policy, an operation, execution is done on a single thread, again, like the sequential execution. However, operations can be interleaved, namely a single thread can process multiple elements at the same time. And this, again, allows the implementation to use vector instructions to accelerate processing, even if it's done within the context of a single thread. The standard also allows vendor-specific policies to be provided, and those policies can use different kinds of accelerators, such as a GPU, FPGA, and dedicated ASICs. Now, one important thing to have in mind is that parallel algorithms do not mean parallel containers, okay? The standard library clearly separates containers from algorithms. And the fact that algorithms can be parallel does not mean that containers are made thread safe. And the reason for that is that thread safe containers, by default at least, would violate the zero overhead principle. I mean, if you're not using parallelism in your program, why would you have to pay the price for being thread safe. Okay, so the parallel algorithms have to bear in mind in their implementation that they are operating on containers that are not thread safe, and so processing have to be to take that into consideration. So how is this, or how can this be done? So, for instance, if you're processing, say, a vector, a regular vector which is not thread safe in any way can still be accessed by multiple threads as long as each thread accesses a different element in that vector. Okay, this is safe according to the C++ memory model. So processing data structures such as vectors is fairly easy. On the other hand, you cannot change, or it's not easy to change the structure of a container. So replacing the underlying array within a vector can cause data races, and even worse, updating dynamic data structures such as sets, maps, and so on that are basically trees that are dynamically arranged according to the data itself that is stored within them. Those data structures cannot be updated in parallel because they are not thread safe. So the algorithms either cannot update them, or need to find some way to make it safe. So one other thing to have in mind is the fact that container is being processed by a parallel algorithm does not make it, again, thread safe during that processing. Namely, if you have two threads, one invokes some parallel algorithm on a container, and the other tries to access that container while it is being processed by the parallel algorithm, then that can potentially create a data race. Okay, so safety is only guaranteed within the execution of the parallel algorithm itself. Okay, moving on. Let's compare the different models we've discussed so far. First, in terms of the source of parallelism, in the unstructured model, it's custom. It depends on the actual use case that, or the problem that your program is trying to solve. In the task-based model, parallelism stems from functional decomposition of processing, whereas in the data parallel model, parallelism stems from the data itself. The state in an unstructured model is basically shared among different threads, potentially global. In the task-based model, the state is delivered by using the promise to future channel. And in the parallel model, the state is the container that is being processed itself. The context in which we execute those models is, again, a custom in the unstructured model. In the task-based model, it would usually be the spawning task will further, or can further spawn other tasks. And in the data parallel model, the parallel algorithm is invoked from a sequential context. Scheduling in the unstructured model is, again, custom. It's up to the particular implementation. In the task-based model, we have a runtime scheduler that uses a task queue. And in the data parallel model, we also have a scheduler that strives to spread the processing among all possible compute resources. And lastly, the status of the different models. So the unstructured model is well established since C++ 11. The task-based model is again, it is also well established, but will hopefully be redesigned. And the data parallel model is being slowly adopted because it has limited support. So the last thing I'd like to discuss is mixing models. So first, let's assume we have some unstructured context. We have a lot of threads that are executing various operations, say by implementing a server. So within this context, in which most cores are used, we can use tasks if we want to hide I/O latency, but we do not have compute resources to invoke some parallel algorithm. That just doesn't make sense, at least unless we can use some additional resources such as the GPU. On the other hand, if within our unstructured context, we are only using few or some of the compute resources, say we're using threads for some background service, then we can certainly invoke tasks and parallel algorithms. However, we do have to be careful with shared state, as with any parallel processing. One thing to have in mind in this kind of situation, the runtime schedulers, whether task-based or parallel algorithms, are not aware of or may not be aware of threads created by the user. Okay, if you create multiple threads, the runtime scheduler might still try to create all possible cores and thus oversubscribe your compute resources. The next scenario is assuming we're using a task-based program, which uses most of the cores in its execution. Namely, it creates a lot of tasks. In this case, within a certain task, it does not make sense to create a thread, or to use any parallel algorithms. We just don't have enough compute resources for that. On the other hand, if we're using tasks just to hide I/O latency or to keep the UI responsive by using a UI worker, then we can use parallel algorithms within a task. Creating threads from within a task does not really make sense. You can instead spawn new tasks. And also using synchronization mechanisms such as mutexes is possible, but doesn't really fit the model, the task-based model. Lastly, if our parallel processing is based on parallel algorithms, then within a parallel algorithm, say your own code provided by a Lambda, there is no point in spawning async tasks or creating new threads. You can use synchronization mechanisms, again, a mutex or some atomics, to access external state, but you have to be careful not to kill the parallelism provided by the parallel algorithm. Okay, to summarize, Andrew Tenenbaum once said, the nice thing about standard is that there are so many of them to choose from. And the same thing applies for C++ parallel facilities. Parallelism is hard, so in general, prefer high-level models. Parallel algorithms provide a simple mental model. They are slowly being supported, but they have great potential with future hardware and new accelerators. Task-based model is underutilized due to its unclear future, but future improvements are certainly to be expected. And in general, the task-based model is key for asynchronous programming. So hopefully we'll see some significant improvements in the future. Thank you for bearing with me thus far. I'm happy to take questions either online or through the Slack channel.